Welcome back to The Explainer. Right off the bat, when something goes wrong on an FPSO, the hidden mechanical reflexes of the ship are literally the only thing standing between normal operations and an absolute catastrophe. We aren't just looking at a floating factory miles from shore. We're looking at a highly tuned survival mechanism. So let's uncover how these failsafes actually work.
Think about the stakes out there for a second. What actually happens when a high-pressure gas line ruptures or a fire suddenly breaks out on the process deck? You're in the middle of the ocean. You can't just call the local fire department. It's an incredibly volatile environment, and a rapidly escalating event can turn a multi-billion-dollar asset into a disaster zone in a matter of minutes.
Ultimately, the difference between a terrifying near miss and a full-blown catastrophe comes down entirely to the reliability of the vessel's safety systems. Today, we're going to dissect the anatomy of this defense. We'll start way out at the macro-level vessel responses and then zoom all the way into the micro-level mechanical failsafes protecting individual pieces of machinery. Okay, let's dive into this. Here is our roadmap. We'll quickly move through the overarching safety net, the emergency shutdown hierarchy, detection systems, emergency power, process machinery protection, and finally, safe marine operations.
Starting with Section 1, the FPSO safety net, which really acts like the vessel's central nervous system. This entire web of interconnected systems is built around one absolutely non-negotiable philosophy, the fail-safe principle.
What's really fascinating here is the human element. We have these manual emergency shutdown and fire panels. Yes, the FPSO is packed with automated sensors constantly monitoring every inch of the environment. But when things go wrong and milliseconds count, these manual triggers give the crew a direct override. Smashing that button instantly forces the ship's automated nervous system to react and lock down the vessel.
Which brings us to Section 2, the emergency shutdown, or ESD, hierarchy. The brain of the FPSO processes an emergency in progressive tiers because, you really want to avoid a total loss of production unless it's absolutely critical to survival. This step-by-step hierarchy is incredibly smart. Step 1 is ESD1, a basic production shut-in triggered by process upsets like high pressure or high temperature. The plant stops taking new oil from the subsea wells, but it holds on to its current inventory. Now, if there's a confirmed fire or gas leak, we escalate to ESD2. This adds what's called blowdown. The ship actively opens valves to vent its high-pressure gas inventory right to the flare stack, specifically aiming to cut the pressure in half within just 15 minutes to starve a potential fire. Finally, if a major accident is underway and we need immediate evacuation, we hit ESD3. This is the total platform shutdown. It commands the subsurface safety valves, the SCSSVs deep down in the wellbores, to snap shut. That physically severs the flow from the reservoir, so even if the surface platform is completely destroyed, the well itself remains safely sealed. All right, moving to Section 3, detection and trigger systems. For the brain to know exactly when to initiate those massive shutdowns, the senses of the ship have to be razor sharp. Just look at the time-bound tension here. You've got fusible fire loops routed around equipment that physically melt under a flame to instantly trigger an ESD. But even faster are the infrared flame detectors. They continuously scan for that specific hydrocarbon flame signature and can initiate a shutdown in an astonishing 2 to 3 seconds. For invisible threats, catalytic bead and infrared gas detectors sound an alarm at 10% of the lower explosive limit. If that gas hits 30% LEL, they automatically trip the ESD. And remember that fail-safe principle? The massive pipeline isolation valves at the riser bases are held open hydraulically against a heavy spring. If the hydraulic signal fails, the spring automatically slams the valve shut. It always defaults to safety. That leads us perfectly into Section 4, emergency power and support. What exactly happens when the main power dies and the ship desperately needs its heartbeat to stay alive in the dark?
Well, the absolute crucial point is this number, 45. In the event of a total loss of main power, these massive emergency diesel generators are mandated to auto-start, synchronize, and take the electrical load of the ship within a strict 45-second window. Just think about that. That's an incredibly tight time frame to bring massive industrial machinery online and wake a dead ship back up. And once those generators do kick in, they have a massive job. They are required to run the ship's most critical life support and safety systems for a minimum of 18 continuous hours. So what exactly gets powered during those 18 hours? These technical specs are basically grounded in pure human survival. We're talking emergency lighting for all the accommodation and escape routes, keeping the fire and gas detection active, maintaining power to the ESD systems and all those crucial valves, running the fire pumps to fight the blaze, and keeping the public address and radio communications alive so the crew can actually coordinate a rescue. Shifting gears into Section 5, we're moving from the macro-level electrical systems down to process machinery protection. We're zooming in on the limbs of the ship, looking at localized fail-safes that protect massive rotating equipment. To run the processing plant, FPSOs use huge gas turbines that burn the associated gas they pull right from the sea, making them completely self-sufficient. We generally see two types. You've got single-shaft turbines, which have the compressor, combustion chamber, and power turbine on one single rotating assembly, simple and robust. Then you have split-shaft turbines, where the power turbine is mechanically independent. This gives you much more flexible speed matching to whatever equipment it's driving. But spinning at these intense speeds introduces some terrifying mechanical risks. Which brings us to the most dangerous operational phenomenon on centrifugal compressors: compressor surge. If the flow of high-pressure gas suddenly reverses, it creates violent pressure oscillations and extreme vibration. Make no mistake, compressor surge can literally rip an impeller apart and destroy the machine in seconds. To prevent this, brilliant anti-surge systems use lightning-fast recirculation valves. The very second they detect unstable flow, they instantly bypass the discharge gas right back to the suction line, saving the machine from instant destruction. That brings us to our final step, Section 6, Safe Marine Operations. Even the routine heavy lifting and cargo transfer tasks require intense, dedicated mechanical oversight. And this brilliantly illustrates how machines literally have to protect themselves with involuntary reflexes. For example, if a driving engine suddenly loses its electrical load, it will rapidly accelerate with no torque holding it back, hitting destructive speeds in seconds. So overspeed trips automatically detect this and kill the machine. Inside those huge diesel engines, hydrocarbon vapor from oil mist can form an explosive mixture. To handle this, spring-loaded crankcase relief valves open at a preset pressure differential to vent the explosion harmlessly, preventing hot oil and metal fragments from blasting across the room. This actually allows for unattended machinery space operations, meaning the engine room can be entirely uncrewed while the control room monitors all the alarms. Oh, and out on deck, those API-2C pedestal cranes use mandatory anti-tube lock devices to physically stop the hook from smashing into the boom tip. Now, take a look at the intricate engineering of this Framo deep-well cargo pump used to offload crude oil. Notice what's missing here: electricity. Because the cargo tanks are explosive hazardous areas, putting electric motors inside them is a terrible idea. Instead, this pump is driven entirely by high-pressure hydraulic fluid pumped down a central pipe from a safe area on deck. It's an incredibly smart way to completely eliminate ignition sources. Let's do a quick recap of this explainer. The vessel is guarded by an emergency heartbeat that has to auto-start in 45 seconds and run those critical loads for 18 hours. The brain uses a 3-tier ESD hierarchy to shut in, blow down, or totally seal the well. Sharp senses like 3-second IR flame detectors and catalytic gas detectors trigger those responses. Down at the micro level, anti-surge systems save compressors from destroying themselves, and clever hydraulic designs like the Framo pump keep cargo handling safe. I want to leave you with this final thought. True engineering genius isn't just in making massive, complex things work under pressure. The real genius lies in exactly how they are designed to safely fail. That fail-safe principle is the invisible shield that protects both the environment and the crew every single day. And that wraps up Module 8 on machinery and emergency safety systems. But the danger isn't over yet. In Module 9, we are going to dive into the invisible threat of explosive gas atmospheres and how we classify hazardous areas under the ATEX requirements to stop a single spark from bringing down the entire ship. So make sure to subscribe, and I'll catch you in the next explainer.